welcome to lecture 9 in the series on noise control in mechanical systems, and I am Professor Sneha Singh from IIT Roorkee. So, to sum up, till now we have studied about sound wave propagation in homogeneous medium, where we studied about the different wave fronts, and then we have also studied about sound wave propagation through a planar medium boundary when wave is incident normal to the boundary, to the plane of the boundary. And we have been able to solve some numericals based on this interaction, but in real life the sound waves can be coming from various directions depending on the location of the source, and they may be incident at various varying angles at different planar boundaries. So, we need to solve and see what happens when a sound wave is incident obliquely or at a random angle to the plane of the boundary, which we will cover in this particular class. And while we discuss this phenomenon, we will come to know of the Snell's law of our wave refraction. We will do some special cases and then solve some numerical problems. So, let us see, this is our medium 1, this is our medium 2 and some sound wave, and again for solving all these interactions we have chosen that the wave is a harmonic plane wave, but the relations derived in general hold true for spherical and cylindrical waves as well, because they can be decomposed or they can be thought of as a special case of harmonic wavefront. So, here I am representing this using this arrow. The arrow represents the direction of propagation of the harmonic wave, and this indicates the wavefront from the top view. Okay. So, this schematic you can look at it in my lecture on harmonic plane wave, where I have discussed what this arrow and the perpendicular things mean. So, what is this notation or what is the meaning of this symbol, you can see in that particular lecture. So, here we see an incident wave at some angle theta I with the normal to the surface, and then it is getting reflected and transmitted. So, let us represent. So, here our incident wave, let us take first of all our x and y axis. This is our x direction and y direction. So, if this is the axis we are choosing, then in that case the incident wave is propagating in the forward x and y axis or the plus x plus y direction. It is propagating in that. So, forward in x and forward in y. So, accordingly for a harmonic plane wave we can represent it as the amplitude into e to the power j omega t minus the x component of the wave number times x minus the y component of the wave number times y. Now, let us see, this is the x component of the wave propagation vector and this is the y component of the wave propagation vector. And what is the propagation vector? It has the magnitude of the wave number, which is omega by c. K1 is omega by c. In our case we have two mediums, so we can represent it as omega by c1, because in these interactions omega, which is the frequency, remains the same. So, both f and omega remain same for such interactions. It is only the speed of the sound that is changing from medium to medium. So, this is our overall k1, and the k1 vector is something with the magnitude as omega by c1, okay, or rather this. Okay. So, for k1 vector the magnitude of this is omega by c1, and the k1 vector direction is along wave propagation direction. So, this is our k1 vector, okay, and as you can see the wave is propagating with an angle of theta I with the x axis. So, this becomes the direction of our k1 vector, and k1x is the x component and k1y is the y component. So, here just so that this thing is visible to you, I am going to erase this part. So, this is our k1x, which is the x component of the k1 vector, and k1y, which is the y component. We are using k1 because it is the k of medium 1. So, what is the relationship between the two? As you can see from the figure and simple trigonometry, k1x is k1 times cos theta I and k1y is k1 times sin theta I. So, let us replace this in the above equation. So, this is the, after replacing, this is the equation we are getting. In the same way, we can do for the transmitted wave. Transmitted wave itself also is travelling in, it is travelling forwards in the x axis and the y axis. So, here that is why we have the negative sign, and we have the symbol k2 instead of k1 because it is in a different medium. So, here k2 is omega by C2. Okay? Just like how we had found out the relationship between k1x and k1y in terms of the overall k1, in the same way we find this, we sort of solve it and we come to this format where it is e to the power j omega t minus k2x cos theta t minus k2y sin theta t, where theta t is the angle between the k2 vector and the x axis. In the same way, let us derive the equation for the reflected wave. Now, as you can observe, the reflected wave, it is travelling sort of forward in the positive y direction, because this is our x and y coordinate, which I will draw here as well. Okay, this is our x and this is our y, and what is happening to a reflected wave? It is travelling in positive y but negative direction. So, that is why we have a plus sign in the x component and a minus sign in y. If you again dissolve this and write it in terms of k1, and here because reflected and incident wave are in the same medium, they both have the same wave number k1, which is omega by c1. So, you resolve it and the wave vector of the reflected wave is making an angle of theta r with the x axis. So, ultimately this is the relationship we get when we resolve its x and y component. Okay. Now, let us see the same continuity of normal pressure on the boundary as we have been doing for the case of normal incidence. So, at x equals to 0, we add up the pressure just on the left hand side of the boundary and the right hand side of the boundary, and the pressure is continuous. There is continuity of the pressure at that point. Hence, P at the limit of x tends to 0 negative should be same as P at the limit of x tends to 0 positive. Okay, we are not suddenly creating a new pressure at this point. So, when you solve it and put the x as 0 in these above equations that we have found, you will see that we arrive at this particular format. Now, in order for this equality to hold true, because here what we have is we have got certain numbers and then we have certain exponential terms and they are being equated. So, for that all exponents they need to be equal so that this equality can hold true. So, in that sense, so we have already stricken off this e to the power j omega t from everywhere, and this is what we are arriving at. So, we equate these exponents. So, all of this has to be equal to each other. So, this thing here, this new equation that we get by equating the exponents on the left hand side and the right hand side. So, every term's exponent has to be the same for the equality to hold true. So, with this what we get from the very first two equations, we get sin theta I is sin theta r, and given that we are dealing with the period between 0 to pi, both theta I and theta r will be same because their signs are coming out to be same. So, what does it mean? That the reflected wave and the incident wave, just like in the case of light waves where they are reflecting from a mirror, they both have the same angle with the normal. When you solve these two equalities, okay, so you write it like this and see over here, this is the final equation we are getting. Sin theta I by C1 is equal to sin theta t by C2. Now, this is very important because this is what we call as the Snell's law for sound wave refraction. Now, there is a Snell's law for light waves, there is a Snell's law which is applied to an electromagnetic wave in general, but because the context of our lecture series is the acoustic waves or the sound waves, we are referring to this as the Snell's law for the case of sound waves. So, let us state the Snell's law. So, verbatim what it says is that when a sound wave, when a sound wave enters a different acoustic medium, the medium having different sound phase velocities, then the frequency remains the same. So, always remember that the frequency of the sound wave is independent of the medium it is travelling in, and the various kind of boundaries and the various kind of elements it encounters on the way. It is independent, it remains the same. The frequency only depends on the source that is creating that sound wave. So, till the source remains the same, it does not matter how it propagates and what part it takes, the frequency remains the same. So, the frequency remains the same, but in this interaction the speed is changing and c is equal to, lambda, which is the wavelength, is c by f. This is changing and this stays the same. So, lambda changes. So, the wavelength changes, and at the same time the direction of the wave propagation is also changing. And what is the manner in which it is changing? It is changing so that this relationship is satisfied. Okay. So, the signs of the angle of incidence and angle of transmission, they are equal to the ratio of the phase velocities in the two media. Okay. So, now we have found this relationship between theta I, theta r and theta t. Let us now again apply the continuity of normal pressure, but now we equate it at one time instance, which is t equals to 0 at the boundary. So, once again this is our equation, okay, and in this equation, because we have already established that for this equality to hold true, all these exponents, they must be same. So, let us just strike them off. This is a common term we are removing from the equation. So, we end up with overall this particular equation here. So, this is the equation of the respective pressure amplitudes. If you divide it throughout by the incident pressure, you again get the same relation, okay, as you got for the normal incidence. Okay. Now, once again have a look at these equations. We have these equations for pressure. Now, let us find out the equations for the normal component of the particle velocity at the medium. The normal, because here in the previous case when it was normal incidence, okay. So, in normal incidence, Vn was same as V, and we did not have to use any cos term in that, and we directly derived everything. But over here Vn is not equal to V. So, the normal component of the velocity in terms of the V would be cos times that angle, it is the cos component. So, velocity is in a particular direction, we want to decompose it along the x axis. So, that is what we get. So, for the incidence angle, the normal velocity is given by, so also we know that V is equal to P by rho c. Okay. So, let us do that. So, this magnitude of V is P by rho c. So, here for incidence wave it is P, we write the format of P here. So, this long expression for Pi we are writing it here, and then divided by rho 1 C1 for the medium 1, and because here the incident wave is travelling forward in space. So, the normal component is along the positive x axis. So, we have a plus sign, and then this times cos theta I. In the same way we can find out the normal component of reflected wave. So, once again we use the equation of the reflected wave, we divide it by rho 1 C1 for that medium, and then cos times of theta r, and then we place a minus sign here because the wave is propagating like this. Okay. So, if you dissolve and find out the normal component along the x axis, the wave is actually propagating in the along the negative x axis. So, the normal component is opposite in direction. So, we put a minus sign here, And how can we write this? So in the same way, we just like how we did the derivation for normal incidence, we will do it the same way. So this can be written as r times of pi max. Okay, in the same way, the normal component of the transmitted wave velocity, once again we write the equation of the transmitted wave, this one here, divided by rho 2 C2 because it is in the medium 2 times cos theta t, and we have a positive sign because the normal component of it is along the positive x axis. Okay. So, this can be written as t times of pi max. You see here what is, we have already found this equation 1 plus r is equal to t. So, here we can replace this t as 1 plus r. Okay. Now, applying the continuity of normal particle velocity at the boundary, let us just equate that. So, we are adding up these velocities. So, one is, so here we add up with the magnitudes. So, plus minus like that. When we did the same thing for pressure, we did not use minus sign because pressure is a scalar quantity, it anyways gets added, but in the velocity we consider the direction as well. Okay. Now, let us remove all the common terms. If you remove that, all of this is that common term. We have already found that these exponents are equal. We remove the common term, and this is another common term we are removing. Okay. So, after removing these common terms, this is the equation we are ending up with. Okay. 1 minus r times of this quantity here and 1 plus r times this quantity. Okay. Now, rho 1 C1 is what? It is Z2. So, rho 1 C1 is Z1 and rho 2 C2 is Z2, which is the characteristic impedances. So, if you replace this, ultimately this is what you are getting, and if you solve by componendo and dividendo, finally this is the result of your reflection coefficient, which is Z2 cos theta I minus Z1 cos theta t divided by Z2 cos theta I plus Z1 cos theta t. Now, if you see here, if you take that this is a generic equation, okay, and normal incidence becomes a special case of this generic equation. So, at normal incidence, which is a generic case, which is one particular normal incidence, a special case of oblique incidence. So, for this generic case, so normal incidence now becomes a special case where theta I was equal to 90 degree, is equal to 0 degree, and this is same as theta r. Okay. So, if you equate this and if you solve using the Snell's law, then ultimately you would end up with Z2 minus Z1 upon Z2 plus Z1. This is for you to solve and see for yourself that the normal incidence can be thought of as a special case of the oblique incidence. Okay, fine. So, now because it is a oblique incidence, the specific acoustic impedance, which is Z, the normal specific acoustic impedance is not same as the characteristic impedance. This is the normal specific acoustic impedance. By the definition, it is the normal component of the velocity, which is P by mod V times cos theta. So, you can say that, and this quantity here is your ZSA or small z. So, the Zn becomes Z by cos theta. So, the same equation that we had found, if we divide by cos theta I cos theta t in the numerator and denominator, this is the expression we end up with. So, this is what? This is the normal specific acoustic impedance of the medium 2, and this is the normal specific acoustic impedance of the medium 1. So, ultimately, you get the same format. The normal specific acoustic impedance, they follow the same format as in the case of normal incidence, and this is in terms of the characteristic impedance, this particular format here. Now, let us do some special cases of oblique incidence. Okay. So, by Snell's law, this is what we are getting. Okay. So, sin theta t we obtain in terms of sin theta I, and cos theta t is under root of this 1 minus sin square theta t. So, this is the expression of sin cos theta t in terms of C1, C2 and sin theta I. So, if these quantities are known, let us consider the first case when C1 is greater than C2. So, as you see here, if C1 is greater than C2, so this term here would always be less than 1. Yeah. So, in that case, the variable inside the expression that is inside this square root would always be positive. So, a square root of some positive number, so which means that in this case theta t is real, and by this relationship theta t is smaller than theta I. So, what is happening here? We are getting a real transmitted wave, and because theta t is smaller than theta I, you can see this particular case here. So, the wave front is bending towards the normal while transmitting into the other media. Now, let us see the second case, which is slightly more peculiar. Here C1 is smaller than C2, okay? And this is our expression. Let us say we have one critical angle. So, theta c is the critical angle in our situation, okay? And this is defined as sin theta c is equal to C1 by C2. So, if you replace this expression here in terms of the critical angle, what you get is cos theta t is equal to under root of 1 minus sin square theta I divided by sin square theta c. And in the first case, our sin theta, our theta I is smaller than theta c. Is theta I smaller than theta c? So, overall this term here would remain smaller than 1, and hence this entire term inside the square root would be positive, and hence we will get a real transmitted wave. Theta t would be real in nature, and by the Snell's law, because C1 is smaller than C2, theta t becomes greater than theta I. So, here what happens in this case? As the wave is incident, it transmits or it is transmitted into the other media while bending away from the normal, as represented here. Now, this is the third case, which is the most peculiar case. What happens here is that now we have once again C1 smaller than C2, but now theta I is becoming greater than theta c. So, in this expression now what happens to this particular thing here? Theta I is greater than theta c, so this would become greater than 1. So, then the entire thing inside the square root, it becomes negative. Okay. So, this means that cos theta t becomes some kind of imaginary quantity. How do we interpret this? We interpret that the incident wave is now getting totally reflected, and we are getting imaginary transmitted wave, which means that in reality there is no pressure wave that is transmitting into the next medium, and at the same time what is happening, because there is no transmitted wave. So, t is becoming 0. So, 1 plus r is equal to 0. So, r is coming out to be minus 1. So, once again that same case we had discussed, when r is minus 1, what does it mean? It means that the wave is having, the reflected wave is having the same amplitude as the incident wave, but now it is shifted by pi. Wherever we are getting a peak in the incident wave, we are getting a trough in the reflected wave, and vice versa. So, they cancel each other out. Okay. So, this is what we obtain. Now, with this understanding, now let us solve one problem on oblique incidence before we close this lecture. Let us say a plane wave is incident at 60 degree. In the boundary between the same air and helium are the same old friends. Okay. So, here the density and the respective speed of sound for the two mediums is given to us. Now, we want to find out the magnitude of reflection coefficient. Now, if it's some student, they without thinking want to solve it, they would just go ahead and start solving, because it's an oblique incidence case. They will first of all find out what is Z1, rho 1 into C1, they will find out certain value, Z2, rho 2 into C2, and then again they will find out certain value, then R they would find as Z2 cos theta I minus Z1 cos theta t divided by Z2 cos theta I plus Z1 cos theta t, like that. and all these calculations they will do. But I have already taught the special cases of incidence. So, before you do all of this manual calculations, you have to see whether it falls under a special case or not. So, here and so whenever the speed of sound in the medium one, okay, it's larger than the speed of sound in the second medium, you can stay cool and you can just go ahead and solve the case, because it will always be the same way. The wave, there will be some reflected wave and transmitted wave, and the transmitted wave will be bending towards the normal, right. But here it is the other way round. Here C1, because our medium 1 is air, medium 2 is this helium. So, C1 here 343, C2 972. So, what is happening here? C1 is coming out to be smaller than C2. So, it's following the special case either 2 or 3. Okay. So, in special case 1, nothing to worry about, but when it is special case 3, then you have to see. So, you have to first ensure that it is whenever C1 is smaller than C2, you have to first ensure that the incidence angle is below the critical angle. So, let us find out what is the critical angle for this particular interaction. Okay. So, the critical angle defined here as C1 by C2. So, let us see this. So, here, so first of all, before doing all of this, we begin like this. Okay. Here the theta c is C1 by C2, which is 343, yep, 972. Okay. So, sin theta c. So, theta c is sine inverse of this quantity here. So, if you solve it, you get the answer as 20.67 degrees, which is way smaller than the theta I. So, what you are getting is that theta I is greater than theta c. Let us see what is happening here. So, if you see, this is the case we are talking about, C1 smaller than C2 and theta I greater than theta c. So, now our angle of incidence has reached that critical angle zone where the transition takes place, and beyond that there is no reflected wave. Yeah. So, you do not need to solve anything, you already found that here this is a special case where C1 is smaller than C2 and we have reached the critical angle and we are beyond that. So, no transmitted wave. So, what is happening here? Since no transmitted wave, what is the magnitude of the reflection coefficient? R is coming out to be -1. Okay. So, in that way you can solve this particular problem, and with this I would like to close this lecture. So, thank you for listening.